All right, so this is the last section of the notes for identities that we're going to learn. We won't get through all of these today. We're trying to just do double angle today. We'll talk about half angle later. So double angle identities are actually derived from those sum and difference identities that we just talked about on the previous page. So we can use what we just learned for sum and difference to come up with double angle. Double angle just means our angle is being doubled. So instead of sine of theta, it's sine of 2 theta because it's double whatever this angle is. Does that make sense? So this is the sine double angle, cosine double angle, tangent double angle. Okay, so if we were to expand this out using the sum and difference identities we just learned, for sine, if both of I can break down 2 theta to theta plus theta, right? Okay, so that would be sine of the first angle, cosine of the second angle, and then do I keep my sign the same or change it? Keep it the same, so it stays plus. And then sine of the second angle, cosine of the first angle. Now here, the first and second angle happen to be the same, so I can simplify, I can reduce this, because these are exactly the same, aren't they? So what is that going to reduce to? 2 sine theta cosine theta. So that's our double angle. Sine of 2 theta is equivalent to 2 sine theta cosine theta. So we're going to write that. There's a box kind of halfway down that is going to box in the identities. So I'm going to go ahead and write that one here. 2 sine theta cosine theta. All right. Now, cosine, if I were to use the sum, cosine sum formula, that would expand to, I don't know why that pen is thicker. Hang on. Cosine of the first angle, cosine of the second angle, and then I do the opposite sign, so minus, and then sine of the first angle, sine of the second angle. That can reduce as well, because what's cosine times cosine? Cosine squared minus sine squared. That's really close to our Pythagorean identity. It's just got a minus instead of a plus. Because these, think of this like if this was x and y. If I said xy plus xy, those are like terms. There's 2 xy's. So if I was combining that algebraically, I would just say 2xy. Because if it was x plus y plus x plus y, that would be 2x and 2y. But because it's the product xy, it's like a single term together. Okay. All right, so now when I go back to that box to write this cosine double angle formula or identity in, I have a bracket. There's actually multiple ways that we can write the cosine double angle. That's just one of them. So I'm going to write that at the top. So it could be cosine squared theta minus sine squared theta. I'm going to skip tangent for now. We're going to go ahead and keep focusing on cosine because this is where it talks about it can be written 3 different ways. Okay, so I went ahead. I'm going to go ahead and write this one again. Now, the way I could rewrite this or manipulate this or use other identities to substitute parts of this, what substitution do you think we could do? Say that again. We could use Pythagorean identity to substitute for one of the pieces here. Not the whole thing together, because there's no way in the Pythagorean to get cosine squared minus sine squared. But individually, I could replace just this piece with the Pythagorean identity. What would just that piece equal? So let me get a different color here. So I would keep the cosine squared minus, and then I would substitute this for 1 minus cosine squared, right? So that's the substitution I just made. And if I do that, I can simplify here. The minus gets distributed, so that becomes -1, and that's going to become positive cosine squared. So I have cosine squared plus cosine squared. That's a 2 cosine squared. And then I'd still have the -1. So that's an alternate way. So I'm going to put that here. Now the third way would be to make the other substitution. Instead of replacing sine squared with the Pythagorean identity, replace the cosine squared. What would cosine squared be equivalent to? So if I make that substitution and keep the minus sine squared, what does this simplify to? There's 2 negative sine squared, so -2 sine squared. So that's the third option. Oops, I wrote cosine again. Let me write that as sine. So the reason it's beneficial to know all of these is because depending on what you're doing, whether it's solving an equation or verifying or simplifying, sometimes you want to have cosine and sine squared. Sometimes you may only want to have cosine squared or only sine squared. So it kind of depends on the situation, which one of those you would use. Okay. All right, let's go look at tangent now. So for tangent, the double angle for tangent, we do the tangent expansion. This is the one that expands to the fraction. And the numerator is the product of tangent and the first angle and tangent and the second angle. And the denominator is 1 minus the product of tangent and the first angle and tangent and the second angle. That can be simplified. In the numerator, that's just 2 tangent theta. And in the denominator, that would be 1 minus tangent squared theta. So that's what I'm going to put in the box down here for my double angle identity. 2 tangent of theta over 1 minus tangent squared of theta. So those are all of your double angle identities. And again, these are not ones that have to be memorized. You will get them. You just need to know how to use them. Questions so far? Okay. So we're going to try this first example down here. Example says given cosine of A is -3/5 and A is between pi and 3 pi halves and sine of B is 5/13 and B is between pi halves and pi. We're going to use that information to answer these questions down here, A, B, and C. Okay, so let's see. If I want to just find sine of 2A, my sine double angle formula says that I can rewrite this instead of 2A being my angle, I can get it to a single angle by writing this as 2 sine of A times cosine of A. I don't know sine of A. I do know cosine of A though. So I'm going to draw a picture. This piece right here tells me what quadrant I'm in. What quadrant is angle A in if it's between pi and 3 pi halves? So I know this is in quadrant 3, so I'm going to draw an angle in quadrant 3. And I know that cosine is -3/5. Well, I know in quadrant 3, both x and y are negative, right? Okay, so from this central angle, what side would be 3 and what side would be 5 if cosine is 3/5? Yeah, cosine would be the horizontal, would be -3 over the hypotenuse would be the 5. Now, because I know those two, could I find the vertical piece? It would be 4, -4. Okay, if you don't recognize the 3, 4, 5 Pythagorean triple, you would just do Pythagorean theorem and you would find that it's 4. And you would need to know that it's negative based on what quadrant you're in. Okay, so if I have this picture of angle A, can I find sine of A? Can I now know what sine of A is? What is sine of A going to be? Opposite over hypotenuse, or you can think of it as y over r. So now I know cosine of A and sine of A, and I can evaluate this. So I can say, okay, 2 times -4/5 times -3/5. Okay, so that's going to come out positive. That's 24/25. Feel okay about that one? Okay, let's try the same thing for part B. I want cosine of 2b. So the cosine double angle has 3 ways of expanding it. I can do any of them. Why don't y'all pick one? Y'all want to do the first, second, or third one? Okay, the third one with just sine squared. The angle they give us is B, and I know sine of B. So that's a good idea because we know sine of B, and so we will use the one that just needs sine of B. So 1 minus 2 sine squared of B is what this will expand to. Okay, and then I know sine of angle B, scroll up a little so I can see it again, is 5/13. And then that needs to be squared. The sine of B is squared. So now I just need to evaluate. You square fractions, you square the numerator and denominator. So that's going to be 25/169. 25, so 50/169. And to subtract, I want a common denominator. So I'm going to rewrite 1 as 169 over 169. So what's that going to leave me with? 119. Uh-huh. Only the numerator, only the 5 squared, because this is 2 over 1. So when you're multiplying, the 2 only gets multiplied by the numerator. Now, had I chosen a different cosine double angle formula, had I chosen the one that needed cosine and sine of B, and I don't know sine of B, I could have done the same thing over here and drawn a picture of angle B and figured out what cosine of B is, couldn't I? I didn't need to yet, so I didn't, but you could do that if you chose the other identity. Okay, what about C wants tangent of 2A? So tangent double angle formula expands to 2 tangent A over 1 minus tangent squared A. Now again, I don't know tangent A. That was not one of the angle values given, but I have the picture of angle A drawn. Can I go ahead and figure out what tangent is based on those 3 sides? What's tangent going to be? Opposite over adjacent, or y over x. So the negatives are going to cancel. It's going to be positive. Tangent's positive in quadrant 3. So 4/3. Okay, and that 4/3 is squared when we're in the denominator there. All right, so that's going to be 8/3 in the numerator. Squaring the numerator and denominator, so that'll be 16/9. So I'm going to do 9/9 minus 16/9. I'm going to change the 1, so I have a common denominator. Okay, and that gives me negative 7/9. And I flip and multiply, right? When I divide fractions. So I'm going to multiply by negative 9/7, which the 9 and 3 reduce, or you can reduce it later. It doesn't matter if you reduce first or at the end. But that's going to be negative 24/7. On the tray over there, on top of the trays. Does that kind of make sense? Okay, we will stop there because we're going to run out of time. If y'all want to be sure and go back and try the sum and difference, check for understandings. If you want to try on this second page, any of these, you can give it a go. They're a little more complicated. We haven't done an example just like those yet, but we'll get to them tomorrow. Don't forget, though, to finish the ALEX. The ALEX is due before midnight tonight. And then tomorrow we'll finish up the double angle notes.